Hello. Oh, that's gonna be, hold on. Hello. Hello. Good morning, Alyssa. Good morning, Charlie. Good morning, Vivian. Good morning, Noel. And you can hear me, I believe. Hello, Daniela. Yes, thank you, Alyssa. Yes. Noel, thank you. Yes, Vivian, thank you. Okay. Okay. Good morning, Jayla. And I know you were very early to arrive. I appreciate it. Okay. I always forget that this class is kind of sometimes not overwhelmingly large. Maybe I'll get used to that now that it's over. Okay, so this is the last, oh, well. Okay, good morning, Farouk. Good morning, Saad. Good morning. I think that's every, good morning. Okay, good morning, Saad. Thank you. All right. And good morning, Farouk. And good morning, Alyssa. And good morning, Vivian. And good morning, Noel. And good morning, Jayla. And good morning, Charlie. And good morning, Daniela. And good morning. Okay. Okay. All right. So this is it, as far as I know. Let me say again, though. Oh, wait. Oh, okay. Okay. Thank you. Totally appreciate it. Doubly appreciate it. Even that counts as having your colleagues back and participate. Even that can be submitted. Great. Thank you. Okay. Okay. It's been a semester. It's been a long semester. I'm tired. You're tired, I would imagine. I wish I were a little bit less tired because I think you deserve nothing but total excitement and celebration today, you guys. Well, almost celebration. I definitely do feel celebratory of you people, seriously. I mean, I'm looking right at my, at the black boxes. And I do feel like I know every one of these names here. Like, I feel like you guys have been here. I know who you are. I mean, I know that you're different people. I know some of your differences. I mean, honestly, I mean, I don't mean to, oh God, that's like a loaded word these days, but I mean, like, I feel like I know who you are. And I feel like this is all going to work out well. I hope, I trust. We've got one more push to get through. That's what we're going to talk about today. But I do just want to say that it's been an honor and a pleasure working with you guys. And I do mean that. And it's always true to a certain extent, but sometimes it's more true than other times. And this is one of those times. So that's another way of saying I very much hope to see all of you. I mean, we're going to get rolling in a minute, but I'm just like wrapping up in advance because this is a wrap up day. I do hope to see you guys in Physics 204 one way or the other next semester. Every semester funny things happen, and every semester life happens, and changes occur, and who knows in what direction. But I'll tell you this, almost invariably, almost no matter what, almost all the time, I teach all the Physics 204 lectures. I guess CUNY First is already out and you're already registering. There still may be changes to professors' names and things like that. Like, never take professor names too seriously, especially in physics. Of course, I love everybody that teaches physics, and I think they're all awesome. Really, and I mean, I know them all very well, very well. But I do hope to see you in Physics 204. I will say, I know it again. I haven't looked at who's registered yet or who hasn't. I know that at least one section of Physics 204 is at 8 in the morning, which is brutal. I know it's crazy that it's at 8 in the morning. There's various reasons for that. It's not usually the case, but it is next semester. I can tell you, if it's not already clear, that the one advantage of the 8 in the morning section is that it is in person, if that is an advantage to you. I will be teaching that one. It's going to be the one day that I can be on campus and the one crazy time that I can be on campus. So I don't know how we're going to get enrollment for that. I don't know who's going to be crazy enough to sign up for it, but I will look forward to seeing in person anybody that can somehow make it to the room, to the lab. at 8 in the morning on Tuesdays. And believe me, when we get there, we'll recognize that it's brutal and we'll be sympathetic to that. We meaning me. I don't think it's going to be the only thing I'm teaching, but one way, but I think, wait a minute. I also think if you're trying to make decisions, I think, most of stuff will be back on campus next semester, as you know, a lot, but not all of Physics 204 will be. There will be some Physics 204 that I'll be teaching remotely like this, I believe. I don't know, whatever, but and you can privately message me when the semester's over. If you want to, as things develop about registration, things like that, I'd be happy to help. But there will be changes. Please don't, I'll update anybody with any changes if they ask me personally, but times and places don't tend to change, but professor names do. Okay, so that's that. So, but I very much hope to see you guys there, and I'm sure everybody's going to end up doing fine in Physics 203. On that, once I get rolling again, I still, like, we're still an exchange of numbers and letters that has to happen. You still can turn in game assignments and stuff like that. And if you have some loose threads out there with homework or stuff, I still have some loose threads that I have to get back to some of you. So you could still get some loose threads back to me. As long as the portal's up, it's fine. I'm going to try to put out, I may have mentioned this, I'm not sure. I'm going to try to put out an Excel spreadsheet this week of like where everybody stands with their grades, like before you turn in the final. I'm going to try to have those loose ends tied up so that you can see where you are and what's going on and what you need to do on the final. I'm going to try before you turn it in. I will say again, I think everybody in this group, this is a small group. As I say, I feel like I know you very well. I think you're positioned pretty well for this final. I think if you do fine on it, you'll do fine in the course. So again, the final should be posted by tomorrow night by 8 p.m. There is another section also of physics that's taught by Professor Walters. So we are coordinating with them on this final. Your final will again look very, very much like the practice final that I'm going to get back to finishing talking about in a couple of minutes. Your final will probably have a choice, or kind of like last time, there will probably be a choice involved. So if you see a problem that seems unfamiliar on your final exam, that's partly because we're coordinating all the classes, but you just choose the problems that you are familiar with and that you like. Okay, I think that's, so yeah, so there'll be, basically what I'm saying is this is the week, it'll be posted tomorrow. You'll have until next Sunday, until the 19th to turn it in. You'll have till midnight of the 19th to turn in your final. Again, you can work with each other. You can go on the web, all that kind of stuff. But that period of time that you're working on your physics final and obviously doing all your other things and working on all your other classes, that period of time, this finals week, is when I'm going to be trying to collect all your grading data and tying up all the loose ends and getting it back to you. So while you're working on your final, I'll be trying to get your whole thing together so that it ends up just being one more number, one final number to put in. And so that ideally there won't be major surprises or shocks or anything when the grades go in to CUNY first. Oh yeah, and one last thing about that too. Sorry, I know none of this is uplifting or interesting, but again, today is the last day, so I'm just trying to put everything together for you. And again, I'm trying to, really my hope is that we just end this semester in a nice, friendly, non-dramatic way, and then we all see each other again next semester. But the other thing is that I do not think, and again, I'm looking at the squares as I say this. I'm looking at your names as I say this, and I don't think there's any name in this group that is headed for any kind of negative result or negative surprise. Okay. Probably, even if you're not getting exactly the grade that even if you're not exactly getting an A or something, even if you're getting a B+ or something like that, you probably know that in your heart as you're heading, or at least as you hand in the final. I don't think there should be any dramatic surprises, and you really will pretty much know before the grades go on CUNY first what to expect. Remember this though. Okay, first of all, remember how it works is your midterm number, your final number, your lab number, they all three get averaged together. I mean, your final lab number that I don't get until the end, but your final lab average from your lab instructor that comes to me at the end gets averaged with your midterms in principle, your midterm score, your final exam score. Those get average. I'm just telling you this for the last time, just so there's no shocks. They get averaged together. That makes one number. Then all of the points that you've accumulated from all of the homeworks, and particularly all of the game things, all of those game credits that so many of you have submitted so many of, all of those make a big pile of points. The pile of points is divided by one common factor, a common factor that's across all the classes. Like, so you might have like 300 points, and then 300 points accumulated of all that homework stuff and everything. And then it's divided by some number, like, let's say 30, whatever that number is the same number for every single student in across the board in both the sections. It'll be divided by some number like 30. So then your 300 points divided by 30. So then you have a total of 10 homework credit points. Those 10 points get added directly to the average that resulted from your midterm, your final, and your lab numbers. And this number that I just used as an example, like 10, is a fairly realistic number. Like that's, I mean, it's different from from person to person, depending on how much homework you handed in, but it's not uncommon at all for it to result in some number like 10. So you get a huge amount of points added to your final test average to credit all the homework work that you've done, which is a lot in a lot of your cases, and to credit all the class participation that you've done, which is a lot in a lot of your cases. And that makes your final grade. So that's just a reminder of how the final grade works, which is why, again, like if you got an 80 on the midterm, you should not be thinking that you're about to get a B- for the course. If you got an 80 on the midterm, likely you're already, if all other things are equal and you're doing fine in lab and you do fine on the final, that you're probably gunning for an A in the course, honestly, if you think about everything I just said. So, and even though this is all boring and I'm boring myself talking about it, I just one last final opportunity to reassure you of sort of how to think about the numbers as you head into the final exam. Again, hopefully this will be somewhere in the middle of the week. I'll be able to get your personal details to you so that you'll see, or you can just, use the details in Google Classroom and do it yourself. But the number the letter that you'll get at the end of the semester reflects something higher than just whatever that number is that you got on your midterm. I'm really saying this all to really tell you, even though, again, I'm almost frustrated to be, oh wait, sorry. Yeah, no problem. Your colleagues totally have your back. You're totally, all good. But thank you. Sorry, this is just like my final, I'm a little bit tired, as you can see, but I want everybody to end this semester with a maximum of serenity and a minimum of stress, to the extent possible. So the last thing I'm saying is this is the important speech I have to give you before the semester closes. I don't think most of you are going to see something very surprising on CUNY first. You do have to wait till they come out. I am usually one of the last. I usually do hand in my grades at the last minute because I don't even get all the finals exams back until the end of final exam period. So it does take me a while. So you'll have to bear with me. Your grade will appear on CUNY first, like the day after they're due, which I think is the 22nd. I can't remember. But when you see your grade on CUNY first, here's the one thing I'm warning you all. It's actually probably the one important part of this whole speech. I don't think you'll be surprised when you see it. And I think if you've done the work in this course and you are who I think you are, you'll not only not be surprised, but you'll probably be content. But if quark forbid, I'm going in, like heading in to hand in those grades, and I uncover some problem in your, like all of a sudden I'm like, oh my God, and this is totally, if I'm like, oh my God, Jalen like never did a midterm, which is totally not true at all. But if I'm like, oh my God, you never even gave me midterm, or, oh my God, like I'm now realizing like 1 minute before the grades are turning in that the final exam is missing, or is like a disaster or something. If all of a sudden I have really bad news that surprises me about your situation, and it's very late in the game, and all of a sudden I have doubts as to whether you could legitimately pass the course or not, but you, whoever you are, and I have not been discussing this throughout the semester because somehow I didn't see it coming, or you didn't see it coming, or something. If that were to happen, and this is, even though I'm staying too long saying this, because we've never had, because this is physics 203, you've never had me before. I want to make this clear. In the event that suddenly I think there's going to be a very negative, big surprise, like a failure or a D or something like that, and I have to hand in the grades, and it is seems too late for us to do anything about this, and too late for me to like warn you and have you correct or get to the bottom of it and ask you like, wait, what's going on here? If that happens, what I do is something that I don't even think we're supposed to do anymore. But what I do is I give you an incomplete. And I need you to hear that. If you suddenly see incomplete, and you're here now listening, if you see incomplete on CUNY first, like when the grades come out, what that means in physics is, please just reach out and write a polite, non-panicked and non-angry email or text to me and just say, oh, I saw there was an incomplete. Can we set up a time to talk and figure this out? And I will say yes. And then we will set up a time to figure it out. And then we will calmly and like non-angrily figure it out. And meaning we'll get to the bottom of what's going on, and there will be an opportunity to rectify it before you just end up with some accidental or scary or unexpected D or F. Okay. That's how when I say incomplete, what I mean is I have an incomplete understanding of what's happening in here. And I need to give this student one last opportunity to come to me and for us to figure it out and see what's missing or why, or do something about this and save the person basically from a surprising F or a surprising D. That's how I use incomplete. I'm not really even sure that we're supposed to use them that way anymore, but that's how I use them. So it does it. And if you've never gotten an incomplete before, by the way, I mean, they're really meant to be for like medical situations, like someone was in the hospital when they were supposed to take the final. So we write incomplete, and the whole idea of incomplete is, as long as it means that there's some outstanding work or something that has to be done. And as long as that work does get, as long as the professor and the student make an arrangement and the work gets in by a certain fairly short amount of time, like before we get too far into the next semester, as long as the work gets in and everybody agrees on it, then the professor hands in a grade change, like hands in a proper grade to the registrar. And then the grade becomes a regular grade, and the incomplete goes away, and the incomplete never goes on the transcript, and it's like it never happened. It's just like a delay of game. Okay. And I'm delaying. I'm spending way too much time talking about this right now, but I do need to make that clear to you that the worst thing that happens, the worst thing that can happen to any of you in terms of a surprise, is to suddenly be surprised by an incomplete. If you get an incomplete, it does not mean game over and you're screwed and you like now never can move on in John Jay, or that it means just reach out to me and we're going to figure out what the situation is and we're going to take it from there. And as long as you do reach out to me, then we'll solve it and you'll have a regular grade. I will also tell you that half the reason I do this incomplete thing is that I will tell you that and there's always a couple people every semester that it happens to, or that I have to do it. And every semester, about 50% of the people who get this incomplete never reach out and never do anything about it and just let it go. And then that does turn into a WU after a certain amount of time, or an F or something like that. And then if they never do anything about it, then it just does degenerate into an effective failure. And that happens in the cases where the person like never really, so you just don't be one of those people. Just reach out to me if you get, okay, anyway, I think you get, okay, can I just say, since I'm spending so much time on this and I didn't mean to, I'm sorry, and we'll get to physics now. Can I just get in the chat, can you just tell me if what I'm saying makes sense, is clear, is okay, do you get it? Like, okay, cool. Okay, thank you, Jayla. Thank you, Alyssa. Thank you. Okay, great. Okay, thank you. Oh, that's everybody. Great. Thank you, Jayla. Thank you so much. Thank you, Alyssa. Thank you, Danielle. I love the totally. Okay, great. All right. So guaranteed everybody who just got that, just heard that, just wrote yes, is the person that's going to get a fine grade in this class. Like, so as long as you stay on top. All right. And if you're okay, good, fine. All right, let's get to physics. Okay. So again, I wish I had a more exciting last class. I know this is not very exciting, but again, this is all about wrapping up loose ends. So what I'm trying to do, I'm going to pick up from where we were. Well, yeah, what I'm trying to do is my goal for the next 55 minutes is to really show you the main thing that's going on in that final exam, which is how could it be that we could take the same pure free body diagram? How can we take the same pure free body diagram and actually resolve it two different ways that lead to two different sets of calculations? And yet those calculations will really lead to the same answer in the end, the same answer. So on the one hand, there's more than one ways to do a physics problem. On the other hand, some are a lot less work than others. And the ones that are a lot less work than others are not always the way that at first seem obvious. So the real art so this is a way of doing everything full circle and saying, you know what, anything you might have felt right at the beginning of this course of like, I sort of get it, but I don't always know how he's going to start or how to start, or I see where he's been, but I never know how he's getting there. That's what we're trying to show right now in our final exam, is that really the art of physics problems is setting them up and making the choices about coordinate systems, the choice of what perspective you're going to look at the problem from, that choice, that you have that choice, because no matter what choice you make, you'll land at the same answer. But if you make it one choice one way, it'll be much easier to get the final answer than if you make it another way. So the whole art of the science is learning how to make these choices. So okay, strictly speaking, this is still just review, just backing up a step, reminding you that we have this block on the rough incline plane. You might want to correct me in the chat if I'm wrong. I'm picturing that the plane, I'm trying to do it the same mental picture as we had last week, where the plane is oriented the way the brown drawing is here. If I flip that brown drawing, I apologize. If our plane used to be going the other way and I've now flipped it, in a way, I apologize, because that might be disorienting to you. But in another way, it might even be that much more helpful if I have, like, what I'm really trying to say here is, it's part of the whole coordinate system thing. Don't memorize my free body diagrams just in the abstract. My free body diagrams are all based on a mental picture of what's actually happening in the physical world, right? So if I'm picturing that the plane is oriented from bottom left to top right, as that brown picture is, then the pure free body diagram would look like that black pure free body diagram looks like. On the other hand, if, say, on the exam or in some other, next semester or something, if you ever ran into an inclined plane that happened to be oriented the other way, like rather than the brown picture, but happened to be going from top left to bottom right, then please understand, and I hope you do, either now or by the end of the week, understand that if the brown picture flips, then the black picture would flip accordingly. Right? Friction is going up and to the right because I'm assuming that some block is sliding down and to the left, as in this brown slide. But there's no law of Moses that says that the brown slide has to go that way, right? So if my slide ever went the other way, which totally could, and maybe even did in the practice exam, like I honestly don't even remember at this point, then my black picture would flip. I hope that's clear. But so, and this is why, by the way, we always, in the 5-step problem-solving method that we do, the first thing we always do, even before we write what is the question, WIQ, we always do diagram and fact pattern. Step 1, DFP, diagram and fact pattern. And that means we do a sketch of the facts, like even before we start doing vectors and diagram and graphs and things that piece apart how to solve the question. We put the facts of the question first so that we know what it is that we're mapping out later on. Okay, so anyway, so that brown thing is the situation. The black picture in the middle of the page is the pure free body diagram of all the forces acting on the object, assuming that brown picture to the right, right? Okay, and again, technically this is review from last Wednesday, but that's our pure free body diagram. Now, we have to have vectors that only point along X and Y axes so that we can say F net equals MA along the X axis and independently but simultaneously say that F net equals MA in the Y axis. So we need an X and Y axis, right? So this is where we were more or less last Wednesday. I've got a choice here. I could make the X-axis be like this, like traditional horizontal, like parallel to the horizon, or I could tilt my X-axis to line it up with the orientation of the plane. This might see, now both will ultimately work if you really believe Galileo. And honestly, again, that's sort of a big thrust of this whole class and of the final exam, is that if you really understand Galileo's principle, if you really understand that you're standing on an Earth that's moving at 65,000 miles per hour past the sun, and yet you never feel it and you never care, if you can actually get your mind around how that could be, it's because you're getting your mind around the fact that that perspective is just a matter of perspective, that the laws of physics hold no matter what perspective you're looking from, no matter what coordinate system you're measuring from, right? So the X and Y axis could be this way or this way. It's just that one might turn out to be more convenient than the other, even if it is less natural or obvious or instinctive than the other. What we're suggesting here, and what you did in the lab in method 1, we're saying, you know what, even though it's not natural, it turns out to be much more strategic to line up our X-axis with the direction of expected acceleration. This block is going to slide down a plane, so we're going to line up our X-axis with that plane so that we can really apply F net equals MA and not have to divide A into a sine and cosine component, right? That's what, so we're doing strategy 1. Like, this is what we said on Wednesday. okay, what we always do is we pick our X and Y axes. We always decide what's our X axis. We always make our Y axis perpendicular to the X axis. I mean, axes are always by definition perpendicular to each other. So we choose our axes and then we always zoom in on the offender or the offenders. What I mean by zoom in on the offenders is any force vectors that are not lined up with an X axis nor a Y axis, they are the offenders. They are off axis. They become the hypotenuse, or each of them becomes the hypotenuse of its own little right triangle, whose legs are the components of that force. One leg is that force times sine. The other leg is that force times cosine. They together add up to make that force. So here, so if the X and Y axis are as I'm saying, you know, if this is the X axis and I'm pointing down, like if, because I expect that the block is going to accelerate down the plane. So if down the plane becomes my X axis and against the plane becomes my Y axis, right? If that's the choice I'm making, because I think it'll be strategic to line up the X axis with the line of acceleration. Then if I look, the offender is mg. Mg is off axis. It's the one that has to be broken up, even though it looks like a straight vertical line. And again, please, this is what what I'm doing right now, I think is ultimately strategic, but I know that because of the benefit of hindsight. Like I'm saying, I have come from experience to know that it'll be strategic to line up my x-axis with the direction of acceleration. But I'm telling you that as a teacher, it's like why I'm the teacher, because I don't think that in the moment, it seems like a natural thing to do. I think it's jostling and confusing. I think when it was first done in your lab, it might have confused you. In fact, if you knew that you were being confused by it, you're probably at a huge advantage in this class. If you were smart enough and attentive enough, I mean, with all due respect, if you were engaged enough to even notice that we were doing this, breaking up the MG, and if you even had a moment where you're like, what? That's good, even though you probably felt it was bad at the time. It's good because it means you notice that it's a little bit unusual and unprecedented that we would take a vertical line and treat it like it was the hypotenuse of some triangle and divide it up into sine and cosine. That is what we are doing. And it is the first time you will have ever done it. This stage in physics is the first time that we do it in physics. So it is unexpected and unnatural and potentially confusing. And again, if you were confused at all when you didn't learn, then Quark bless you. If you totally missed it, please note now. It's like, it's not obvious, even if I'm trying to make it sound reasonable. What it is sensible that we look at the situation, we say, you know what, it's going to be best if we need an x-axis and we need a y-axis, we need to be conscious of what they are. If we call the x-axis the line of acceleration, then mg is the one arrow in this diagram that needs help. It is not on an axis. It needs to be broken up into components that are on an axis. So we zoom in on that offender called mg. So I'm going to zoom in on it, right? And by zooming in, I mean now I'm going to say that when you fall in this when you're pulled in this direction called straight down, you're really being simultaneously yet independently pulled in two directions. You're really being pulled, if you're being pulled down on an inclined plane, you are really being pulled somewhat, excuse me, you're being pulled somewhat, actually, I'll just use a different color. Sorry. Well, yeah, no, okay. You're being pulled somewhat along the plane, and you're being pulled somewhat into the plane or against the plane. Notice, right? Like tilt your head. I'm saying this is a right triangle of which mg is the hypotenuse. It is a tilted right triangle. You have to tilt your head to see it, because that's what we're saying. You got to tilt your head to watch the acceleration that's going along this tilted axis in the first place. But if you're so I'm just zooming in on mg right now. I'm zooming in and I'm saying it really consists of two components that are added tip to tail to make it. To be pulled down is really to be pulled down and left, plus down and right, if you think about it, right? And so one of these is hypotenuse times, one of these is hypotenuse times sine of the angle. The other is hypotenuse times cosine of the angle, right? Just like any other vector triangle that we've ever made from velocities or from displacements, like prior material. Right, because this is SOHCAHTOA, right? So sine equals opposite over hypotenuse, and cosine equals adjacent over hypotenuse, and tangent equals adjacent over adjacent, and tangent equals opposite over adjacent. But that means in physics, if you think about it, right, it means that opposite always equals hypotenuse times sine, and adjacent always equals hypotenuse times cosine of the angle, et cetera, like that's right. So each leg is some fraction, some portion, some percentage of the overall hypotenuse length. So the only question is, or the question is, if drawn like this, like which one is the sine and which one is the cosine? Well, the way to answer that is SOHCAHTOA, whichever is opposite the angle is sine, and whichever is opposite the, whichever is adjacent to the angle is cosine. But which is the angle? Like, and I'm trying to go now, please also note that much of what I just said for the last 20 minutes is a little bit repetitive or a little bit recall from last week, or hopefully refreshing, whatever. So if you understood last week, you might have been tuning in with half a brain, if that much. Now, just note, I want to say something now that I have not said before. Like, because you don't want to just memorize mg sine theta or mg cos theta. That's in fact a big part of what this final exam is trying to get you away from. Don't just memorize. I need you to understand which one is which and why, especially because at any moment anybody could change the diagram around and then things will change around. Sine is always opposite to the angle. The question is, in this right triangle, which is the angle? By which I mean, which of these two missing angles in the right triangle is the theta that is given in the first place? What's given in the first place is the angle of inclination, the angle of elevation, the angle at which this plane has been pulled, to the angle to which this plane has been pulled relative to the horizon. The original given known angle refers to the angle drawn in the original inclined plane picture, like in the brown picture to the right, and then I don't know why the angle will pop in any second to the left. Oh no, my board just, oh my God, it's coming back, it's coming back. I don't know why that's happening. There's an internet thing, it's coming back, I promise, I think. Hold on. I'm gonna try to get this back, but while I'm getting it back, so sorry, I don't know why. It should come back. Okay, everything's on a major delay. Okay, so you see that angle. By theta, we mean the angle in the original apparatus, the angle of inclination between the horizontal floor or lab table versus the slide itself. Now, the question is, how does that angle have to do with this triangle, this force triangle that I'm drawing? Well, the simple, the straightforward answer is that angle is this. The angle theta is the one down here in this triangle. And it's important to know that. If I think that, so I'm saying with this theta right down here that I just drew in this blue theta, it's not just a random theta. It's not just any old angle. It's the angle that you're given in the problem. If I thought that the angle that you were given in the problem were the upper angle in this triangle, the other one, then I would get my sine and cosines wrong. Okay, and we want to get our sines and cosines right. So I am telling you that this angle here is the angle we got in the problem. And if you believe, and just believe that for a second, I'm going to explain it. But one of them has to be, and it is this one. If you believe that it's this one, well then sine is opposite over adjacent. So the side opposite this angle gets sine, and the side adjacent to it gets cosine. That's where we're getting the sine and cosine from. However, and again, this now when I'm talking is like not anything I said last week. I mean, this is the subtle, tricky part. Honestly, let me say again to this group in particular, because I think you're a very fine group. If you've been studying this at all or looking at this, or you even remember it from high school, which is fine, or you were thinking about it in the lab, if ever you got to the point where you sort of knew what was going on, or you were even bored, like you thought you really knew what was going on, but if you ever got to the point where you're like, yeah, I get all this, I don't quite know why this one is sine and this one's cosine, but I get that one has to be one and the other is the other. So I don't really get where, like my lab instructor got that this one is sine and this one's cosine, but okay, I'll accept that. Like that's my only confusion and I'll move on. If that was your confusion, if even for a moment, then again, I applaud you. If you were smart enough and clean enough in your thinking to recognize what you didn't get, which is always the trick in science, if you knew what you didn't know, and you even knew for a minute, like, I don't really know why he got sine here and cosine there. And I'm sort of thinking about it, but I still don't get it. Whether you worked it out or you went on the web or you gave up, no matter, I mean, hopefully you tried things, but I'm telling you, if you were bothered by the issue of which one is sine, which one's cosine, then first of all, welcome to the club. Like, good. That does not mean you're stupid. It does not mean you're off base. It does not mean you're out. It means you are thinking like a physicist, because that is the bothersome issue here. Like, it so totally has an answer. It can be explained more than one way. But if that's your big issue of which one is sine and which one's cosine, then I have to tell you, good. And by the way, continue to focus on that and think about that, because and when we get into physics 204, that basic issue of resolving vectors and knowing which one is sine and which one's cosine, it sort of never goes away. It's always a niggling issue in physics, and the better, and it is part of the art of the science. The better you can get and the more comfortable you can get with that issue of sine and cosine, the better you will get. But it first starts with, let's all recognize that is an annoying issue. You are not crazy if you're worried about it. You should worry about it. So now let me tell you, I hope that makes sense. But really, the sine cosine thing never goes away. And also, please don't run away from it. If you're finding it annoying, just remember, all of us find it annoying. Like, don't like shut down over it. That's where you should spend your studying time, is like really trying to get straight when to make the sine and when to make the cosine, because we can flip things around. Like if the inclined plane just flips, or if we just give an angle from the top rather than the bottom, then the sine and cosine will flip. So it's something you do want to be able to understand and not just memorize or accept on blind faith. So here's my point of how I knew which one was sine and which one was cosine. A couple of different ways. Number one, you can just do Euclidean geometry. I mean, this is the long way, is you can. Let me try this on the next. By the way, and this is a real issue, because subtext of what I'm saying is, despite what you might have thought in like 10th grade math or something like that, don't think that cosine always goes with X and sine always goes with Y. That's just not true. I mean, and you can see here, it's not true. Sine does always, I mean, the cosine is not always on the X-axis and the sine is not always on the Y-axis. They totally aren't in this case. Sine always goes with opposite and cosine always goes with adjacent. That is true. You can take that to the bank. If you were to memorize anything, you would memorize SOHCAHTOA. That is reliable to your dying day. I mean, till eternity. But the real question, if you're following me, is, I mean, you can always do SOHCAHTOA, but the question is, which is the angle in the triangle? Like which of these two non-right angles in this triangle did I know to be the actual same theta as was given in the problem? That's the annoying issue, is like, where's theta here? Okay, so one way you can know Yeah. Okay. Okay. One way, this is the long way. I'm not saying you would want to do this every single time if you're in the middle of the exam, but just to, if nothing else, explain to you where I got it from. If you think about it, this, the original angle in black, theta, the angle we're given is the angle we're given, right? And if you think about it, the angle down here at the bottom, like that's the angle that I'm trying to figure out in my triangle, right? I just flipped the pages. We're on a major internet delay here, but that angle at the bottom is the angle that we're trying to figure out, right? Well, I'm saying if you just zoom in on this whole thing, if you really think about it, if I don't know how to put it in words other than this picture, but if you think about it, the angle at the top right must be the 90. I mean, assuming that all the angles of a triangle equal up to 180 degrees, and assuming that in any right triangle, then the two non-right angles have to together equal 90 degrees, like I am assuming that, right? Then the angle at the top right of this right triangle must be 90 minus our original theta. And this, what I've drawn here, this red thing is one big right triangle. So the angle at, so it, right, so if the angle at the top right of this big right triangle is 90 minus theta, then the angle at the bottom must be theta. Okay, to some of you, hopefully that's convincing. I mean, that's like my proof of why that angle at the bottom is the original theta, and therefore the vector component across from it is across from theta, is opposite theta, and therefore gets sine, etc. So hopefully for some of you that at least proves why the angle at the bottom is theta. Am I saying you have to do all this work every single time you do an exam? No. This is maybe why you can believe what I did, or it is, if you have all the time in the world, you can do this to figure it out. But but as long as you have some reason to believe me now, let me tell you the shortcut or the short method. Okay. If there's, even though it seems like I'm taking a really long time on this, I am. If there's one little takeaway I'd like you to have going into physics 204 or into physics or any other mathematical quantitative science for the rest of your life, maybe even chemistry, if there's one thing you all know, yeah, I mean, you got to know trigonometry. It never goes away. Everybody hates it at first. It becomes a lifeblood after a while. thing about trigonometry that you all know is that sines and cosines are very, very related, very, very similar, almost identical, but just different enough to be annoying. And one of the hard matters of trigonometry or relating trigonometry to actual physical world is always sort of like, when do I use a sine and when do I use a cosine and what's the difference? What, remember this, if nothing else, for the rest of your, well, yeah, and in the attempt to remember, what's the sine of 30 degrees? Oh, it's 1/2. What's the cosine of 30? Oh, it's radical 3/2. Which one is which? And blah, blah, blah. If there's anything you want to remember, besides the unit circle, for the rest of your life, is ground the whole thing in sine of 0 is 0. Cosine of 0 is 1. But sine of 0 is 0. Like, it rolls off the tongue. It's almost like a snake talking. It's just sine of 0 is 0. One way I even remember with students long ago, I used to, younger students, we used to just, if you're trying to know the difference between sine and cosine, just always remember, sine is super, cosine is crappy, like, honestly. Or sine is, pardon my Hebrew, but sine is super, cosine is counterintuitive, if you want to say. What I mean by that, they both work the same. They're both the same type of function, all that. But sine is the one that does what you would do if you were on a desert island by yourself, inventing math, making up all this for the first time. You would make functions the way sine is. What do I mean by that? I mean that the sine of 0 is 0. And then as the angle gets bigger, sine gets bigger. It's totally natural. It's totally reasonable. It's what you would want. Bigger the angle, I mean, at least with acute first quadrant angles, the bigger the angle, the bigger the sine. If the angle is really small, the sine is really small. If the angle is so small that it's 0, then sine is so small that it's 0. Sine is super that way. Sine is the function that actually kind of like makes sense, or you could say sine is sensible that way. Cosine is the one that's the opposite. Cosine of 0 is 1. And as the angles get bigger and bigger, the cosine gets smaller and smaller. Or you could say cosine is confusing. But if you're ever going to be confused by trigonometry, be confused by cosine. Like, let that be your confusion. Sine is our friend in these contexts. So what does that have to do with anything? What it has to do with 20 minutes left is, if you think of sine that way, that sine, it just spits out a fraction or a percentage or a portion that gets bigger as the angle gets bigger. Sine, in fact, is like an indication of how big your angle is. The bigger the angle, the bigger the sine. It's just literally a signpost on the size of the angle, only the numbers don't go linearly. So what does that mean to us? It means, look, now I know I know this seems repetitive. I know I've drawn this like 40 times in the last week, but now I'm really trying. I really want you to look at this component diagram that I'm drawing now. And also, I know I have 18 minutes. I want you to also see the alternate choice, but look at this choice for a minute. And I know many of you have just like memorized it at this point. So you're like, yeah, we know this already. But I'm really asking you, as part of our final exercise, not just to memorize this, but actually understand it, so that you can do well with the final exam and for the rest of life and all that. What I'm saying is, we break up mg into sine and cosine. Sine because it's opposite that angle, cosine because it's adjacent to that angle. So back in our free body diagram, we take out the mg and we put in its two components. And notice I've moved them around. Like the whole thing about vectors is that every vector, all of the information stored in that vector is in its length and in its orientation. That's all the information, is how long it is and where it's pointing. Where it is on the page is not part of its information. So we can move them anywhere we want on the page, and we don't mess with the vector image information. And that's actually the power of vectors, is that we can move them around and put them where we need for different purposes. So I'm drawing all my vectors, all tail, like all of them are starting with their tail at my object, that my mass of interest, right? And I'm saying that this mass of interest is, rather than just saying it's being pulled down to the center of the earth, I'm saying that what the earth is really doing is two jobs. It's pulling the mass somewhat along the plane, and it's pulling it somewhat into the plane. The weight of the block is to some extent keeping it supported on the plane itself, keeping it from flying and levitating off the plane. That's mg cosine theta, i.e. some portion of its weight, some fraction of the object's weight is being supported by the plane itself. Some of it is keeping it from levitating off the plane or breaking into the plane. Some portion of the weight, mg cosine theta, is balancing with the normal force to keep the block in contact with the rough plane. The other component of gravity, mg sine theta, is what sends it along the plane, sends it accelerating along the surface. Now look, what I'm saying is, how did I actually decide which one's sine or which one's cosine, or how can I actually know that I'm right about the sine and cosine assignment? Because sine of 0 is 0, because sine gets bigger as the angle gets bigger. What this picture tells me is something I think that's very logical, which is that as the plane gets bigger and bigger, the component of weight, the fraction of this object's weight that sends it along the plane, gets bigger and bigger. In other words, it's going to accelerate at a greater and greater rate down the plane, the steeper the plane is. If like, this is what we're calling the x-axis. This is the direction of actual acceleration. The steeper the plane is, the bigger sine is, the more the thing will accelerate along the plane. In fact, in the limiting case, if the plane were 0, and if the angle of inclination of the plane were 0, the block would not accelerate along the plane at all. Sine of theta would be 0, mg sine theta would be 0. The block would just sit there. On the other fraction, mg cosine theta, would be mg times 1. All of the weight of the block would just keep it on the plane. So as the plane gets steeper and steeper, a bigger portion of the block contributes to downward, a bigger portion of the block's weight contributes to downward acceleration, and a smaller portion of the block's weight contributes to balancing or being supported by the normal force, i.e. less and less of the block goes into squeezing and contributing to friction. You see what I'm saying? The assignment of sine and cosine actually makes sense if you think sine super, cosine crappy. If you think sine of 0 is 0, it makes sense that sine is the one that sends you along the plane and cosine is the one that keeps you into the plane. Now, it also makes sense for this reason, with 14 minutes left. If this is my component axis, now this is my component diagram. I know I've drawn it before, but I'm really trying to like break it down for you now. This is my component diagram, assuming that I've chosen these tilted axes. Choosing tilted axes might seem like a strange thing to do, but here's why it's a very powerful thing and a very simple thing to do. Once we make that physical leap and we have this diagram, now we continue with the method. We're now ready to apply F net equals MA individually on each axis. And with this picture, it's fairly straightforward and comparatively easy to do that. We'll do just like we did before. Let's go. if you were following me last week, then one benefit you get from that, we could save time now, is you'll understand why from now on, since we did last week, whenever I do physics from here on in, and once I've finally set up my component diagram and I've got stuff going on 2 axes and I have to apply F net equals MA to each axis individually, what I always do is I always start with the axis that I think I don't care about. I always start with the Y axis, even though we're ultimately looking for the acceleration along the X axis. That's what we're ultimately always looking for. I start with the Y axis because I've learned from last week that on the Y axis will often be the normal force, which I will need to determine the friction on the X axis, right? So I'm always going to start. So I start with the Y axis. You can do whatever you want, but you can be most efficient if you start with the Y axis. So I say, so I'm just going to the next page. I say F net in the Y axis equals M times A in the Y axis. So I look at the Y axis. What do I have in the Y axis? I've got normal force going in one direction, and I've got mg cosine theta going in a different direction, the opposite direction. So it gets a minus sign. So I'm adding up all the forces in the Y axis, right? But they're going in the opposite direction. So one of them gets a minus sign. So there's my Y axis statement. And then I say, aha, in the Y axis, if I've set this up for this strategy, we've got 11 minutes in this strategy where I deliberately aligned up the X axis with the direction of acceleration. That means by this setup, in the Y direction along the Y axis, there should be no acceleration, right? In the Y axis, as I've set up, in other words, the block is not flying off the plane, nor is it crashing through the plane. That Y axis, there's no acceleration. I know this because I set up my axes that way. All the accelerations along the plane. So that right side equals 0. Therefore, I can say this fairly straightforward with these axes, right? And now I can use so now I go to the X axis, right? And where am I getting this information from my Y and X axis? Just directly from the picture. So the whole point of this picture. Like I've spent weeks on this. It may seem so stupid, but I spent weeks on just like learning how to set up these pictures because all the information is coming from the pictures. Oh God, this thing is on such delay, but it's flipping. But yeah, that picture that is circled in red, like the Y axis is N minus mg cosine theta. It's like really straightforward once you have the correct picture. The Y axis is everything in the Y axis. And the X axis is everything in the X axis. And I just put minus signs for anything that's going in a different direction. So it's mg. So the X axis with 9 minutes left is mg sine theta minus F. That's my X axis, right? Just straight from the picture. I would never know that if I didn't have a correct component free body diagram. And component means, notice there's nothing in this. I mean, there's a bunch of arrows, but none of them is anywhere but some kind of axis. That's what all my work has gone into. Okay, so I say mg sine theta, and down is reckoned positive here because that's where we assumed the thing was going to accelerate, minus friction equals ma times the X axis. Now, if this thing is sliding, we're assuming it's already moving for this context. We're assuming that we're talking about kinetic friction, right? So by friction, we mean kinetic friction, and that is mu kinetic, mu sub k, times the normal, right? That's what kinetic friction always is. So I'm going to substitute that in. I'm just going to the next page. Right, okay. okay? The normal we got from the y-axis. Again, that's why we had to do all this work to divide things up into axes. So we substitute in mg sine theta minus mu k times mg cosine. That's what we just started. I didn't even emphasize enough. On the y-axis, what we learned is that the normal force is supporting a portion of the weight. How much portion? Well, it depends on the angle. The bigger the angle, the smaller the portion of the weight is being supported by the plane. The more you're making this plane like a wall, the less you're supporting the object. And the less, therefore, you are creating friction. That's what we're saying here. Okay, so we have that. So now we can factor out an m. So this is a complicated, but we're looking for m. I mean, sorry, no, we're not. We're looking for a. A equals all of that left side but all divided by m, and you could factor out the m. The m is in every single term, so you could factor it out. Now, we have 6 minutes. What I'm saying is the acceleration for the inclined plane, it looks a little complicated, but it's not really that the answer. This is, and then if there's numbers, you plug in the numbers. But what we're really saying is we're saying the steeper you make the angle, the bigger the sine, so the more the actual weight of the object will make this thing slide down quickly, but minus this term due to friction. Like the steeper you make the angle, the more the weight of the object will directly contribute to how fast it goes down, and the less its friction will contribute to how much it goes down. It's a minus sign. That I don't know if that answer looks complicated or not complicated to you, but what I really want to say, but it's a hard problem to deal with incline and friction and gravity all in one problem. We just did it. The real ultimate lesson with 4 minutes left is as easy or hard as you might have thought that was, or as clear or as not clear as you think it is. I think that's the clearest way to do it. I think that represents the clearest, fastest way to do it by rotating your axes to line up with the direction of acceleration. With 4 minutes left, if we go back to our original pure body iron with 3 minutes left, and we do the other choice of axes, the one that might seem more natural and more instinctive if you don't think all this through, if we choose axes like this, just regular old X and Y, then if you look at the picture, we'd have to break up normal and we'd have to break up friction. We wouldn't break up gravity, break up those two, and the acceleration would be broken up also. So with just 3 minutes left, let me just set up for you. Let me show you that this will ultimately land at the same answer, but it's going to be a lot more work. Look. And you'll have to think this through as you're doing the final. I mean, this is your job, but MG won't be broken up. It's perfectly fine. It's just straight down. But friction, if it's going up and to the right, means it's going somewhat to the right and somewhat up. It'll have a cosine component and a sine component. Normal also, if it's going up and to the left, is going to go somewhat up and somewhat left. It will also have a sine and cosine component, but they can't be the same because normal is perpendicular to friction. So they're going to be, you have to think this through, but the normal, the cosine will be purely vertical, which is unusual. But if you draw the angles and do the trick that I said, if you decide the cosines of the sines by the strategy that I spent this whole class showing you, you'll see that this becomes the component picture. And with 1 minute left, what does that mean? Then that means ultimately, when we do F net equals MA along each axis, okay, I can go back to this page in a second if you want, but it's also on the front page, that F net equals MA, and this is the last thing, we have 1 minute, along the X axis would be N sine theta minus minus F cosine theta equals MA cosine theta, because even A has to be divided up now because it's not straight along the axis. And Fy would have to be N cosine theta plus F sine theta minus mg equals MA sine theta. And here, and I'm done. It's 12:05. I'm going to put down the cannoli and put down the gun, whatever. You know what I'm saying? Here you would do the exact same method. You would write out those statements. Then you would look at the y-axis and rearrange everything and solve for n to get. You have to get n to then plug into the x-axis to solve for friction, and then solve for A. It's a lot more work. You could totally do it. You do the same method as the other method. And if there's no friction, then it's easier to do, but both are easier to do. But what I want you to see is it's one method all the time for all of physics. One method gets you the right answer. One method gets you the right answer, no matter which coordinate system you choose. But you must be in a coordinate system, so you must choose. All choices lead to the same answer, but some choices get you there a lot more conveniently. That is the art of physics. That's what you're seeing on the final exam. This is with friction. That's as hard as it gets. There may or may not be friction in the actual final exam, but this is what you do. I am done. I know it's a lot. Obviously you can, and again, here I'm putting, for my last thing, I'm putting my number one more time in the chat just in case. So if you have questions at all from here on for the next week of any kind, feel free to text me. If it's like a long thing, then we'll set up an appointment, or you can email too, but just tell me who you are. If you text me, I think you've been great. I think you will be great. I wish you well. I hope to see you next semester. So goodbye. Thank you very much. I'm here just in case there's questions, but I'm turning off the recording and all that. See you. Yes. Oh, thank you very much. Yes. See you next semester. Thank you, guys. See you next semester. Definitely. Thank you. I totally appreciate it. Okay. Awesome. I'm turning off. See you next semester. Indeed. Awesome. Awesome. Yes. I like your attitude. All of you. Yes. See you next semester. Excellent. Excellent. And have a good break. Yes. Happy holidays. All right. I'm turning off the